sin cos1，对啊，考试会给表。Yeah. Okay. So I guess this is our last class, and it will be our final review. And just like a midterm review, final review, we don't go into specific final problems. We basically go over what we talked about in the last half of class, and hopefully this refresh some of your memory. Okay. So let's go back to chapter 3. So in the middle part of class, we spent a lot of time talking about those 4 different Fourier transform pairs. So, so there are differences in continuous time and discrete time, and in whether the time domain signal is periodic or aperiodic. So we start our Fourier transform pairs in chapter 3, where we say we have a continuous and periodic Fourier series. Continuous time periodic signal, and they can be expressed as this harmonic series. Okay, so this is a Fourier series, and those AK was the coefficient for your harmonic complex exponentials, and but now we know that those AK also correspond to the Fourier coefficient or Fourier transformed signal in the frequency domain. Okay, so the AK is the Fourier transform for a continuous time periodic signal. Then in chapter 3.6, we have this the Fourier transform for discrete time periodic signal with some period big N, and they also transform to some AK. And but in this case, we see that there is a very strong symmetry or duality between AN and X of N and A sub K, because we think AK as also a discrete time signal in terms of K, then both X of N and AK is periodic with period big N. And this is why this discrete time for the Fourier transform for discrete time periodic signal, also called discrete time Fourier transform. Also called discrete Fourier transform. And that's a bit confusing because there is also discrete time Fourier transform, which is this chapter 5 case. But anyway, let's not worry about the notation. And then in chapter 4, we go to the Fourier transform that most people talk about. This is the continuous time Fourier transform of a continuous time periodic signal. But we also see that for periodic signal, you can also express that as a Fourier transform, just with frequency domain signal having a whole bunch of spikes. It has a delta function. Okay. So this is a continuous time Fourier transform. You transform from this X of t, which is a time domain signal, to big S of J omega, which is a frequency domain signal, where this omega is your frequency. And then lastly, there is a discrete time Fourier transform, which transform a discrete time signal to a discrete time signal to this actually a continuous signal in frequency domain. And but because this signal is discrete time, the input signal is discrete time, so in the frequency domain we have this big X of e to the j omega being periodic with period 2 pi with respect to omega. This is a recurring thing. This is a thing that keeps happening whenever we have a discrete time signal. We see that you have a discrete time signal, then in the frequency domain your signal is periodic with period 2 pi. This is a concept that we keep emphasizing. Okay. And here we have some duality errors because of the back and forth transformation formula has a strong symmetry between them. So this X of t and the big X of j omega has duality, and X of n and AK here has duality, and then this x of t ak and x of n big X of e to the j omega has duality. Okay. And let's go back to this is actually in the range of a meter, but let's still do a review. So this is the Fourier transform and the inverse Fourier transform formula in big font. So we have Fourier transform formula, big X of j omega is this integration of x of t e to the minus j omega t dt. And then inverse Fourier transform, we go from big X of j omega to small x of t is x of t equal to 1 over 2 pi integration minus infinity to plus infinity big X of j omega e to the j omega t d omega. And those formula will be given in the text sheet. Okay. And so that is continuous time. Then we have discrete time Fourier transform, and x of n is still 1 over 2 pi, so we have a comparison to continuous time. So this integration is basically the same, except that big X of e to the j omega, big X is now periodic with period 2 pi. So instead of integration from minus infinity to plus infinity in continuous time case, we now have integration over some range 2 pi in the discrete time case. So this is inverse transform. We only integration over period 2 pi. And then the analysis equation is basically the same. So instead of integration, you have summation because we have a discrete signal. So big X of e to the j omega equal to summation n from minus infinity to plus infinity x of n e to the minus j omega n. And and this big X is called a spectrum or frequency domain signal, which we keep using. Then there is this symmetry that we see many times. Okay, so those are the conjugation symmetry and the time reversal symmetry. I think we test this a bit in midterm, but they might still appear in final. Okay, and for Fourier transform, they are all similar, so we just have an example of the discrete time Fourier transform here. And I think the two most important things to remember is the first two. So you need to remember that basically what happened in time reversal. So we have that if you if you do time reversal in time domain, you also have time reversal in frequency domain. So if x of t is even, then big X is even, and if x is odd, big X will also be odd. Okay, and there is also conjugation symmetry for there is also conjugation symmetry for the Fourier transform, and okay. I guess it's easier to see here. So if you have conjugated in your time domain signal, then for this big X, you need to have a minus sign before your omega, and also a star on your big X. Oh, sorry, I was saying this was discrete time, but this is also the continuous time Fourier transform. Sorry. Okay, so this table was from continuous time Fourier transform. But anyway, x of t real will mean x of j omega equal to x star of minus j omega. So you take conjugation in the time domain, and you get the same signal, so you get the same big X. And also, if you are purely imaginary, then you will get minus x star or minus j omega. Then you can combine those four to see all four possibilities. Okay, so you can have even odd, real, or imaginary, and then your big X of j omega will have the corresponding four. And I think it's nicer to memorize the first one. This is probably the one that you see most often, or maybe the first two. So if you are real and even, small x of t is real and even, big X of j omega is also real and even. This is very nice to remember, and the next one is a bit nice to remember. That is x is real and odd, then big X is imaginary and odd. And here we have more analysis about if you have a real signal, what are the all components, etc. Okay, and I think we have said for a real signal, for example, we have a real signal, and the even part will correspond to the real part of big X, and the odd part will correspond to the imaginary part of big X. Okay, those were the analysis we talked before. And here are properties. So property will be tables, and I think the table is still going to given. So let's just look through them very quickly, and you can see, some of the conjugation symmetry here, etc. Those are properties, and so properties for the continuous time Fourier transform. Then we have properties for the discrete time Fourier transform. Okay. And so it's nice to you can look through them more carefully when you do review yourself. Okay. And then we have Fourier transform for periodic signal. So the table we have at the very beginning, we say Fourier transform is for a periodic signal, but we can expand the definition a little bit to include the periodic signal too by using the delta function. So we say if you have some e to the jk omega t, then although you cannot really do direct integration, but by the Fourier transform back and forth, by the Fourier transform back and forth property. So if you think the Fourier transform and the inverse Fourier transform are close for this e to the jk omega t, then we think that 2 pi delta omega minus k omega naught is the Fourier transform of e to the jk omega t. Then for periodic signal, you can always write them as this linear combination of e to the jk omega naught t. So you can Fourier transform them to linear combination of those delta functions. Okay, so this is the Fourier transform for periodic signal. This is for continuous time case. And for discrete time case, we can also do similar thing. So if your x of n is written as this summation k, ak e to the jk 2 pi divided by n, 2 pi divided by big N times small n. So this is the Fourier series representation of your discrete time signal x of n. Then we say that now the frequency domain signal need to be periodic with period 2 pi because this is discrete time. So instead of one impulse for each e to the jk omega naught t, we have an impulse train for each jk omega naught t. So if you write this as okay, so we say big X of e to the j omega is this same linear combination of 2 pi times delta, but we also say this is periodic, so this keep repeating itself with x of e to the j omega equal to big X of e to the j omega equal to big X of e to the j omega plus 2 pi. And you have a nice way to express this as one simple equation is instead of summing k from 0 to n minus 1, you just say summation k from minus infinity to plus infinity, and have your ak being a periodic signal. So ak equal to ak plus n. Okay, and yeah, so the result will be a linear combination of impulse train like this. And so basically there will be n different ak, and they keep repeating itself for every n slots, etc. Okay, and then the big application of Fourier transform is you can use it to solve the differential equation, and we say that we use Fourier transform to solve differential equation by taking Fourier transform on both sides, and then this differential just give you extra powers to the j omega. So this dk dt to the k become j omega to the k, and you move things around. Then if you think your system is LTI, then your big H is big Y divided by big X, which will equal to this summation is a linear combination of bk. So those bk for x of t times j omega to a k divided by ak times j omega to a k. So this will be a rational function of j omega, and we say we can do partial fraction expansion on this rational function of j omega to get a whole bunch of partial fraction in terms of j omega, and we can look up the table to invert those partial fractions. Okay. So we have a whole bunch of something over a plus j omega, something plus over b plus j omega, etc. And you can look up the table and invert those. And if you have a higher order partial fraction, you can also invert them with a more complicated formula. Okay, But then we say, okay, so now go spoiler a little bit. So this was using Fourier transform to solve differential equation. But the big constraint of this is that big Y, big X, and big H should need to actually exist. So yeah, so the Fourier, in particular, that means the Fourier transform integration need to converge, and your small y, small x, and small h need to be basically absolutely integrable. Okay, and that don't always happen, and that's why we can use the Laplace transform to solve our differential equation. So instead of doing Fourier transform, we can do Laplace transform. And Laplace transform has a very similar formula. So this d to the k dt squared give you this s to the k, and you can express this h as big Y divided by big X as a rational function of s. Okay, and you can similarly do partial fraction expansion and get this into partial fraction of s and do inverse Laplace transform. But the different part for Laplace transform is that Laplace transform, instead of just the algebraic part, you also need to specify the RC. Okay. And that's consistent with our differential equation, because by differential equation itself, it don't tell us, don't specify the whole system. So the auxiliary condition will tell you, hopefully will make the system still LTI and tell you the ROC. And I think a good example of this is when you have the initial race condition, then we'll prove that the differential equation with initial race condition is LTI and causal. So that will satisfy the both two constraints that we need. So first, this is LTI, so this equation makes sense, and also it's causal, and from causal you can infer the RC of our Laplace transform here, and the RC will be the rightmost pole, right to the rightmost pole, etc. Okay, and emphasize once again, it's important when we use this formula, and this formula is important to remember that our system needs to be ROC, otherwise, well, even if you are not ROC, you are not LTI, sorry, the system needs to be LTI. And so even if your system is not LTI, obviously you can still brute forcefully calculate this, but for non-LTI system, this system function h doesn't mean much. Okay? It don't really determine your system response, etc. Okay, and so that's the differential equation, and then we have some Fourier transform pairs. Okay. And I guess one of the pair that we like a lot is this square wave and the sinc function. So we have is a periodic square wave. Sorry, this is a periodic one. But basically, square wave will Fourier transform to the sinc function. That's sine theta over basically sine theta over theta. Okay, and yeah, yeah. This Fourier transform. We have a sinc function, Fourier transform to this square function, and square functions Fourier transform to sinc function, and this is a duality. Okay, and here we group a box some relations that's useful for solving differential equation. Those are the inverse Fourier transform for the partial fractions. Okay, and then we also have, for discrete time case, we have the difference equation, and similarly we can use the discrete time Fourier transform to solve difference equation. So this big Y divided by big X equal to summation bk e to the minus j omega jk omega divided by summation ak e to the minus jk omega. And those e to the jk omega comes from this time shifting property. So you do time shift on your signal, you get by k, you get by minus k, you get this HR e to the minus jk omega. Okay, so this will be a rational function e to the minus j omega, and once again you can do partial fraction expansion to solve this. Okay, And here we just emphasize once again that big X of e to the j omega is periodic with period 2 pi. And also we can use the Z transform to solve the difference equation for for example non-stable system. So if you do Z transform, then big H of Z equal to summation bk z to the minus k divided by summation ak z to the minus k. And once again, this don't tell you the ROC, and you need to infer your ROC from our constraints. And also you need to check that your system is LTI. Okay, and here are a table for discrete and Fourier transform pairs. And here we have the Fourier transform for periodic signal, etc. And and here we have those those partial fractions with e to the minus j omega, and with different powers. You can use them to do inverse Fourier transform. And I guess later we'll have the similar page for Laplace transform and the Z transform, and you can use them to solve the differential equation too. Okay, any questions so far? Those were review for Fourier transform and a bit of Laplace and Z transform. I guess then we can go to Laplace transform, and as we said, Laplace transform is basically Fourier transform, but instead of e to the minus j omega, here we have e to the minus s here. So instead of purely imaginary exponent here, we have any complex exponent here. So s equal to sigma plus j omega. Okay. And nice important concept to remember is that x of s is just equal to, so if s is some real part sigma plus j omega, then x of s is just a Fourier transform. When you are fixing on some sigma, x of s is just Fourier transform of x over t to the minus sigma t. Okay. And also there is this ROC concept that's very important. So x of s only converge on part of the s plane. That's compared to Fourier transform, where we think is either converge on all omega or converge on none of the omega. And we have this very basic example that we use throughout the whole chapter 9. That's these two time domain signal that Laplace transform to the same algebraic expression 1 over s plus a, but they have different ROC, and we see here that ROC is an important part of your Laplace transform. So this x e to the minus at u of t transform to 1 over s plus a with ROC being greater than minus a, and then we have this minus e to the minus at u of minus t, Laplace transform to 1 over s plus a, also 1 over plus a, but its ROC is to the left of u minus a. Okay. And those two expressions are also important because they are used to do inverse Laplace transform, because you can usually expand your rational function to a lot of partial fractions involving 1 over s plus a. Okay, and here we see a right-sided signal transform to right-sided ROC, and a left-sided signal transform to a left-sided ROC. And we have those properties on ROCs of Laplace transform. We list them all here, and but I guess the ones to kind of memorize. If you are finite duration, then ROC is everything, and if you are right-sided, ROC will extend to right. If you are left-sided, ROC will extend to left, and if you are two-sided, then ROC will contain a strip. So most of the time it's a strip, and there is a most one strip. And also, if your Laplace transform, if your big X of s is rational, then your ROC will bounded by poles or infinity. Okay, and the next property is just calculated from the previous properties. Okay, I guess there is property 1.5 that we didn't include here. Property 1.5 says that the ROC consists of those sigma where your Fourier transform exists, and basically this thing is absolutely integrable. Okay, so we'll update the 1.5 here later. Okay, 1.5. And here is some picture of possible ROC. So this is some basic problem that might appear in final, and I think already appear in homework. So I will tell you that on the S-plane there are some poles for this Laplace transform, and ask you, and if it's a rational function, then you can figure out all of its possible ROC, and basically the ROC will be bounded by poles. So here if you have two poles, then ROC can be this rightmost ROC, or in between ROC, or this left-sided ROC. Okay, and then we talk about inverse Laplace transform. The first method is to do this counter integration, and we don't. I guess there is a homework problem that we try to do this, and this is basically doing an integration of similar to Fourier transform, but you just need to pick a sigma that's inside ROC. Okay, and then the second method we use more is this partial fraction decomposition. So we have a rational function, then we can also always do this partial fraction decomposition or expansion, and expand into partial fractions. And for example, here this 1 over s plus a, s plus 1 times s plus 2 become 1 over s plus 1 minus 1 over s plus 2. And this s plus 1 and 1 over s plus 1 and 1 over s plus 2, we can use one of those two Laplace transform pair to do inverse Laplace transform. Either invert to this left-sided, right-sided signal or left-sided signal. And which one is true depends on your ROC. You need to see whether your ROC is to the right or to the left of your pole 1 and minus 1. Okay, and so for this example, you have 3 different ROC, and you have 3 different inverse Laplace transform. Okay, and then if your rational function has a numerator more degree than denominator, then you need to do some division. And for those positive power of s, you will inverse Laplace transform to singularity functions. So either delta function or there's a singularity function, unit, doublet, etc. Okay. Okay, and here we have a table of properties for Laplace transform, just for you to see, and also pairs of Laplace transform. And I guess here we can group together those that's important for doing inverse Laplace transform. So it's those things. Yeah, should be these ones. This is 1 raised plus a to some power, etc. So those are the partial fractions. Okay, so they can be used to do inverse Laplace transform, and also therefore also be used to solve the differential equations. Okay, and then we have these two properties that can be inferred from the ROC of Laplace transform. That's stability and the causality. And we see that LTI system is stable if only if ROC includes a geometric axis, kind of like this. And for causality, this is a bit more complicated. And we say is so if it's causal, then the signal is right-sided, then ROC is right-sided. But the ROC is right-sided doesn't mean the system is causal. Might be just right-sided. But if the system is rational, then right-sided, and then causal is equal to ROC being right-sided. 有问题吗 Question? Okay. And so this is stability and the causality, and so stability intuitively look at this, your ROC include the geometric axis, and the causality intuitively correspond to this RC being recited like this. And also we talk about this blood diagram for representing our system. And this is a bit funny because we talk a lot about RC, but with these blocks we don't really see the RC. So we kind of just assume the system is causal. And we see how to use those blocks, some small blocks to piece together the system function you want for your system. Okay, so for example, this is feedback loop. This is kind of the basic situation. This feedback loop will give us that the system has a system function h1 divided by 1 over h1 plus h2. And so if we put the integrator here, we see that this is how we can construct big H equal to 1 over s plus a, with with a basically being this number here. Okay, you have 3 here and the minus sign here. You have this h equal to 1 over s plus a. Okay, and we see that we can construct systems with more complicated system function or more complicated differential equation like this. Okay. So we have a differential equation is basically this 1 over s squared plus 3s plus 2. Then we can have direct form like this. We have 2 integrator here. And then we can also have a cascaded form where we factor the denominator. So we have first system give us 1 over s plus 1, second system give us 1 over s plus 2. And we can also do partial fraction expansion and get this parallel form. So the upper part give us 1 over s plus 1, and the lower part give us 1 over s plus 2, etc. Okay, and so some way to give a system function you want with block diagram. And lastly, we have in terms of Laplace transform, we have this unilateral Laplace transform, which just Laplace transform by integration from 0 minus, where this 0 minus means that you also include any singularity at 0. And because you integration from 0 minus, for unilateral Laplace transform, we actually don't need to specify RC because RC is always the rightmost RC. Okay. And we have properties for unilateral Laplace transform, and the most important one is this differential property, and it's very different because it gets this HR minus x0 minus term. Okay, and this is compared to a differential property for Laplace transform only give you HRS. And with this differential property, we see that it has an important application with solving initial value problem. Where initial value problem means that you have a differential equation, but now we are not having this initial race condition. We say we have initial value conditions. Initial conditions means that at some point, and it's usually 0. Okay, it's nicer if you have 0 because our unilateral Laplace transform start from 0. And anyway, if you have initial conditions start from 0, so you have our output being some value at 0 and the differentiation of output being some value at 0. So this beta and gamma. And together with this differential equation is initial value problem. So you have the initial values and the differential equation, and you ask what happened. You have some input, what's the output. And we see that this can be done with the unilateral Laplace transform together with this differential property. So we have a differential property tells us that the second order derivative equal to, if you do unilateral Laplace transform, give us this s squared big script y minus this initial condition times s minus gamma, and this dy dt unilateral Laplace transform to this s squared big y minus y is 0 minus, so s squared big y minus 3 beta. Okay. And then from here you see that we can write big Y some expression for big Y, and also unilateral Laplace transform small x. Okay, and so everything together, this is some equation with big Y and small and S, so we can express what's big Y, and then we see that big Y is a linear combination of those beta, gamma, and alpha. And if we are given a value of the alpha, beta, and gamma, then we can once again inverse unilateral Laplace transform to solve the time domain signal for Y. Okay, and okay, let's finish 15 minutes. We should be able to finish this. So we have the Z transform. So Z transform is basically Laplace transform for discrete signal, and its equation are here. So big S of Z equals this to this summation from minus infinity to plus infinity, x over Z to the minus n. Okay, and we see that the Fourier transform. So Z transform on some radius r is the Fourier transform of the signal times r to the minus n. Okay. And we see there is a strong connection between Laplace transform and the Z transform. So we say the Z transform is basically Laplace transform, but you wrap a straight line into a circle. So the j omega axis becomes a unit circle. This is because Z is basically exponential e to a s. And we also want this wrapping around circle because we know for discrete time signal, omega is periodic with period 2 pi. So instead of having this omega being periodic every 2 pi, we wrap it into a circle. So it will be periodic with respect to omega by construction. So we have e to yeah, by construction. So omega changes 2 pi, then you change it from 0 to 2 pi, and you work on this circle from 0 to 2 pi back to the original point. Okay, and so for right-sided signal in right-sided RLC in the Laplace transform will mean outside-sided RLC for the transform, and the left-sided RLC for Laplace transform will be inside the RLC for the transform. And then two important signal, this exponential decay signal, a to the n, times u to the n will Z transform to 1 over 1 minus a Z minus 1, with RLC being outside Z greater than a, and absolute value Z greater than absolute value a. And then there is also the inside signal, minus a to the n u of minus a minus n minus 1. This will Z transform to similar thing, so it's 1 over 1 minus a Z minus 1, but we'll have RLC being absolute value of Z less than a. Yeah. And then we have properties of Z transform, and the first property is that the RLC will consist of rings, and once again we have property 1.5 says that those RLC consist of those R such that xn r to the minus n is absolutely summable. And then once again with property 2 says that RLC don't have pole. And the property 3 now is different. So we have x of n being finite duration. REC is basically entire Z plane, but there are 2 points that you need to take carefully. That's Z equal to 0 and Z equal to infinity. And then RLC contains Z equal to 0 if only if this upper bound n2 is less than or equal to 0. And RLC contains infinity if only if this lower bound is greater or equal to 0. And yeah, most of the time only one of them can satisfy, and only signal that satisfy both of them is for both n1 and n2 equal to 0, and your x of z is just a constant. Okay. And then you have property 4, which is similar to Laplace transform, says that the right side sequence you have RLC being the outside. But also you have property 4.5 says that RLC equal infinity if only if this left-sided bound is greater or equal to 0, and basically means that the signal is causal, which is be misnomer. Okay, but says that, And also property 5, we have the left-sided signal. The RC is inward, but include 0 if only if this N2 is less than or equal to 0. Okay. So those analysis on infinity and 0 is something that we only take care of for the transform. Okay. And here I have some schematic picture. So this is RLC for right-sided signal, this is RLC for left-sided signal, and this is RLC for two-sided signal. And for two-sided signal, once again, we say it's intersection between right-sided signal and left-sided signal. So most of the time, it will be a ring. Okay. And then if the transform is rational, then your RC is bounded by poles or extend to infinity. Then, okay, we have 10 minutes, so we go a little quicker. And then there are ways to do inversely transform. And the first way is to do integration. You can do either contour integration or just this integration like Fourier transform. But the important thing to remember is that you need to pick R that's inside RC. Okay, so X of n equal to R2. Yeah, so this is you pick R inside RLC and do Fourier transform for X of n R to the minus n. Okay, and then yeah, and then multiply the R back. Okay, and so this is integration. We don't usually do this, and most of the time we do partial fraction expansion. We say that, for example, we have this RLC, and basically we want to do partial fraction in terms of z minus 1. And we want to express into those partial fractions with terms like 1 over 1 minus a z minus 1. Then we determine whether RLC is outside of this a or inside of this a, and inverse transform to the right-sided signal or left-sided signal. And for higher order, we can inverse to beta C. And and I guess something nicer here is also we didn't put it here, is that sometimes you can do partial fraction expansion, not totally, because we also have the time shifting property that says that if you have extra power over z on you have some extra power over z on top, you can just use time shift property to get rid of it. Okay. And I guess let's jump a little bit. Yeah. So because so this time shifting property is very nice to when you try to do inverse z transform, because you can absorb extra power over z just into time shift of your signal. Okay, so sometimes you don't need to partial fraction expansion every z on the top. Okay, and then also you have the power series expansion. That is just look at this z transform formula. Big X equal to summation x over n to a minus n, and then if your big X of z is already in this power series, then you can just read out x over n from the coefficient to your z to the minus n. And to make things look like a power series, sometimes you can do long division or you can do Taylor expansion. And we're seeing that in the examples, you need to be a little clever to do your expansion, etc. Okay, so we have the properties of z transform. And some of the transform pairs. Here we have the pairs that are useful for doing inverse z transform. Okay, and once again here we have some extra power over z, and if you don't have that, you can use time shifting property to adjust that. And also we can analyze the causality and the stability by the RC of z transform, and we see that causality is actually easier. You just need to see whether your RC includes infinity. If your RC includes infinity, then your C-set is causal, and vice versa. And if your C-set is rational, then you can check this including infinity a little easier. So first your RC needs to be outside, and also your h of z need to go to be finite when z goes to infinity. So the order of d need to be greater or equal to order of n here. And stability is the same. Is your RC need to now include a unit circle. That's compared to this RC include the geometric axis for Laplace transform. And we also have the bar diagram representation for z transform. And this formula is the same. If you have h and h1, h2 here, then we get this h1 over 1 plus h1 times h2. But for constructing difference equation, the construction look a little different because in the continuous time case, we use a lot of integrator. But for discrete time case, this time delay element is very stable, so we like to just use a whole bunch of time delay element. And here is one differential equation that can be written in 3 different forms. So we have direct form, cascade form, and parallel form. And the idea is similar to continuous time case. So continuous time case for direct form, you just write down, try to construct the differential equation, and the cascade form, you try to factor the differential equation, factor the system function, and the parallel form, you try to do partial fraction expansion of the system function. Okay, and we jump ahead a lot. And I guess we are missing a slide for unilateral z transform. But basically, unilateral z transform is just z transform but summation starting from 0. And here is a property table that we say we'll put it into slides. So we also update the slide for chapter 10 and have this table 10.4 for unilateral z transform. And okay, I guess here we have the properties, but we don't have the most important property. And oh no, I found it. Okay, so the most important property here is this time delay property. So the time delay property will be used to solve our difference equation, and it's a little bit weird because we got this x of -1 here. But anyway, that's how we do it, because in terms of initial value problem for difference equation, we actually give you the value of y excuse me, a few steps before the initial value, and a few steps before the initial point n equal to 0. And so for example, we have this difference equation with initial value at -1 being some beta, and then we can apply this time delay property of our unilateral z transform and get our big Y equal to this -3 beta over 1 plus 3z minus 1 plus alpha over 1 plus 3z minus 1 times z 1 minus z minus 1, etc. So this is a linear combination of rational function in terms of z minus 1. And beta is this initial value, and alpha is this input here. Okay. So if I give numbers of alpha and beta, then you can calculate what is y of z in terms of partial fractions, and then inversely transform to get what's y of t for the y of n for this difference equation with the initial condition. Okay. And yeah, so we are about right in time. So that's I want to say for the final review. I think we cover most of the thing. If no question, then I think we can stop now, and good luck on your final on next Monday. Okay, yeah, so that's it. So thanks for coming to class, and good luck on your final.